The Amish have been keeping chickens alive through brutal winters for over 300 years without a single electric heater, and their survival rate puts modern farmers to shame. Most people assume that keeping chickens through winter requires expensive heating equipment, automatic temperature controllers, or at minimum a reliable power source. The Amish have none of that. What they do have is something far more valuable: generations of hard-won knowledge about how nature actually works. And once you understand their methods, you will never look at a chicken coop the same way again. Before we get into the techniques themselves, we need to talk about something most chicken keepers completely overlook. The Amish do not reject technology because they are behind the times. They evaluate every tool and innovation based on one specific question: does this strengthen or weaken our community? Grid electricity gets rejected not because it does not work, but because it creates dependence on outside systems. Gas-powered equipment sometimes gets approved because it serves the community without tying it to external infrastructure. That distinction matters because it shapes every farming decision they make, including how they heat their coops. At the center of Amish farm life sits one animal that most people underestimate: the chicken. Not as a novelty or a hobby, but as a cornerstone of daily survival. A typical Amish farm runs anywhere from 30 to 50 birds. During peak laying season, 40 hens will produce roughly 30 eggs every single day. That adds up to nearly 11,000 eggs across a full year. These are not pets. They are a living, breathing food supply and trade resource. Losing even a fraction of that flock to winter cold is not just an inconvenience, it is an economic disaster. That pressure is exactly why Amish chicken keeping methods are so refined. Every technique has been stress tested across generations, revised, passed down, and improved upon. Nothing survives in their system unless it actually works, which is why what you are about to learn deserves serious attention, even if you have access to every modern convenience they deliberately avoid. Now, here is something that surprises most people when they first hear it. Chickens are not cold weather animals by origin. Their ancestors came from the tropical jungles of Southeast Asia. These birds evolved in warm, humid environments with year-round heat. Over thousands of years they have adapted, but that adaptation only goes so far. Expecting a chicken to handle a brutal northern winter without any support is a bit like dropping someone raised in a tropical climate into an Alaskan winter with just a light jacket. What happens when temperatures crash below freezing? Egg production does not just slow down, it can stop entirely. Studies show that when temperatures drop below 20 degrees Fahrenheit, egg output can fall by up to 40%. Nearly half your daily eggs gone. And the eggs that do get laid during extreme cold tend to have thinner, more fragile shells, which makes them far less useful. Cold stress also hammers the immune system. A stressed, cold chicken becomes vulnerable to respiratory illness and other diseases in the same way a sleep-deprived, run-down person catches every bug going around. Different breeds handle cold differently. Chickens with large combs and wattles, those fleshy protrusions on their heads, are especially vulnerable to frostbite. And yes, chicken frostbite is a real and painful condition. Those parts of the bird are not just decorative, they play a role in regulating body temperature. When they get damaged by frost, the consequences are lasting, not temporary. Here's another fact that catches people off guard. Chickens burn significantly more calories in cold weather just to maintain body temperature. During winter months, a laying hen may need roughly 1.5 times her normal daily feed intake. That is a jump from about a quarter pound of feed per day to nearly 4/10 of a pound. The bird is not overeating. She's just running her internal furnace harder to stay alive. In regions where temperatures regularly dip below zero, unprotected flocks can see mortality rates as high as 30% during harsh cold snaps. In a backyard flock of 20 birds, that means potentially losing 6 chickens to the cold alone. The birds that survive prolonged exposure to extreme cold can also suffer reduced fertility come spring, meaning fewer viable eggs for hatching and a smaller flock going forward. Understanding why cold hurts chickens is the foundation. The Amish built on that foundation with techniques that cost almost nothing and have worked reliably for centuries. The first one involves something most people walk past every single day without giving it a second thought: rocks. Specifically, heated rocks placed strategically inside the coop.
Before you dismiss this as too simple to be effective, consider what these stones are actually doing from a physics standpoint. Dense stone materials like granite, basalt, or soapstone absorb heat during the day and release it slowly over many hours. The right stone, warmed thoroughly, can radiate steady heat for 6 to 8 hours after being removed from its heat source. That covers most of a winter night. The Amish do not use just any rocks they find lying around. Selection matters. The ideal stone is roughly the size of a loaf of bread, heavy enough to hold significant thermal energy but light enough to be carried safely. A well-chosen stone weighing around 10 pounds can release consistent warmth for 6 to 8 hours inside a properly insulated space. Place 4 or 5 of those throughout the coop, and you have a natural heating system that requires no fuel, no electricity, and no maintenance beyond daily rewarming. During the day, these stones sit in sunny spots or near the household wood stove. By evening, they are wrapped in old burlap sacks to prevent direct contact with the birds, then placed around the coop's perimeter. Some farmers arrange them to create small warm zones where chickens can gather without pressing directly against the hot surface. The temperature check is done by hand. If you can hold your palm against the stone for about 5 seconds before pulling back, it is at the right level for the coop. Too hot and you risk overheating the space. Too cool and the effort is wasted. This slow, steady heat release is actually superior to many modern heating options in one important way. It does not create sudden temperature swings. Chickens handle gradual temperature changes much better than they handle rapid fluctuations. The stone method produces what farmers call a heat bank effect, a slow, even release of warmth that mirrors natural temperature patterns far more closely than a thermostat-controlled electric heater cycling on and off all night. The Amish also think about thermal mass during the construction of the coop itself. Large, dark-colored stones are built directly into the south-facing wall, where they absorb maximum winter sunlight throughout the day. A properly built heat wall containing 200 to 300 pounds of stone can maintain interior temperatures 10 to 15 degrees warmer than the outside air, even without any additional portable heated stones. That is permanent, passive heating that requires zero ongoing effort once it is built. There is also a community dimension to the stone heating routine that is easy to overlook. On the coldest nights, heating and placing stones becomes a shared activity. Children learn the technique from parents. Neighbors help each other during extreme cold snaps. Skills transfer naturally through participation rather than instruction. The method does not just heat coops, it builds the kind of practical knowledge that holds communities together across generations. From an economic standpoint, the math is striking. A quality set of heating stones requires one upfront investment in selection and preparation. With basic care, those same stones can serve a family for decades. Some Amish households use stones that have been passed down through multiple generations. Compare that to the ongoing operating cost of electric heating systems, and the case for the old method becomes surprisingly strong. But heated stones are only one piece of the system. The ground beneath the chickens is doing something remarkable all on its own, and most modern chicken keepers have never heard of it. It is called the deep litter method, and the core idea runs completely against the instinct most people have about cleanliness. Instead of removing chicken droppings and soiled bedding regularly, you layer fresh material on top and let the whole thing build up over time. Start with about 4 inches of clean, dry material, straw, wood shavings, or dried leaves. Each week, add another inch of fresh bedding on top. By the time winter hits its peak, you have a floor layer 8 to 12 inches deep. Here is what happens inside that layer. Chicken droppings mix with bedding material and beneficial bacteria get to work breaking it all down. That decomposition process generates heat. Not a huge amount, but consistent, steady warmth at floor level. A well-managed deep litter system can maintain floor temperatures 10 degrees warmer than the outside air on cold nights. The heat generation is not even the most impressive benefit. The microbial activity inside a healthy deep litter system creates what farmers call a living floor. Beneficial organisms outcompete harmful bacteria, reducing disease risk naturally. Chickens raised on deep litter systems consistently show stronger immune responses and fewer respiratory problems than those kept on regularly scrubbed bare floors. The biology of the system works in the birds' favor.
Moisture management is the key variable. Too wet and the litter produces ammonia instead of healthy decomposition. Too dry and the bacteria cannot do their job. The target consistency feels like a well-wrung sponge. Squeeze a handful and it should hold a loose shape but crumble easily. Every few days, stir the litter, especially around water stations where spills accumulate. 100-square-foot coop needs roughly 15 to 20 minutes of attention per week to maintain the system properly. Different bedding materials bring different strengths. Pine shavings absorb up to 4 times their weight in moisture and break down relatively slowly, making them excellent for maintaining the right humidity balance. Straw is less absorbent but creates more air pockets, which support bacterial activity and add insulation. Many experienced farmers layer both, shavings on the bottom for moisture control, straw on top for warmth and biological activity. The bacterial action in deep litter actually increases during colder temperatures, which is the opposite of what most people would expect. As outside temperatures fall, the decomposition inside the litter ramps up, producing more heat precisely when it is needed most. It functions like a biological thermostat, self-regulating in response to conditions. Measurements in well-managed systems show up to 8 additional degrees of warmth at floor level during the coldest winter nights. Come spring, the system delivers one more payoff. A winter's worth of deep litter from a modest coop produces enough rich compost to fertilize roughly 2,000 square feet of garden. That compost is dense with nitrogen and beneficial microorganisms, ideal for heavy-feeding crops. The chickens have essentially created free fertilizer while heating their own home. That kind of closed-loop efficiency is exactly what Amish farming is built around. Now that we have covered what happens at floor level, it is time to look at the walls, ceiling, and the structure surrounding the birds. Because keeping warmth from escaping is just as important as generating it in the first place. A poorly insulated coop can lose up to 30% of its heat through gaps, thin walls, and uninsulated ceilings. The Amish address this without hardware stores or modern building materials. Their approach starts with the walls themselves. Traditional construction often uses a double wall design, 2 separate wall layers with a gap of 4 to 6 inches between them. That gap gets packed with natural insulating material, most commonly straw. Straw packed tightly into a wall cavity creates hundreds of tiny air pockets. Trapped air is one of the best insulators available. A 6-inch straw-filled wall delivers insulation performance comparable to modern fiberglass bats, and straw is available on virtually every farm at near zero cost. Where sheep are part of the farm operation, wool scraps get saved specifically for coop insulation. Wool manages moisture differently from straw. It naturally repels water on the surface while absorbing it internally, and unlike straw, it retains its insulating properties even when damp. Wool can absorb up to 30% of its own weight in moisture without losing its ability to trap heat. For exterior walls exposed to winter humidity, that combination of properties is extremely valuable. Door design gets careful attention in Amish coop construction. Many coops feature 2 separate entry points, a full-size outer door for human access and a small inner door sized specifically for the birds, typically about 8 by 10 inches. This creates a buffer zone that dramatically reduces heat loss every time someone enters or exits. The small chicken door alone reduces heat escape by up to 75% compared to using a single human-sized entrance. Gap sealing is done with a traditional mixture of clay and straw called chinking. This material gets pressed into every crack and joint between boards or logs. Over time, chinking actually performs better than many synthetic sealants because it flexes naturally with the wood as it expands and contracts through seasonal temperature changes. It does not crack and pull away the way rigid foam or caulk often does. The roof demands special attention because warm air rises and exits through the top of any structure. In traditional Amish coops, loose straw gets packed into the rafter space and held in place with chicken wire, creating a thick insulating layer directly above the bird's roosting area. Some designs allow extra straw to be added during especially cold periods, essentially giving the coop a thicker blanket during the worst of winter. Windows present a specific challenge. They are necessary for light and ventilation, but they bleed heat constantly. The Amish solution is removable straw panels, 2 to 3 inches thick, that fit directly into window frames at night or during severe. These panels can cut heat loss through windows by up to 60%.
During daylight hours, they are pulled out, allowing sunlight to warm the interior. At dusk, they go back in. Simple, effective, and free. Floor insulation gets addressed through a combination of methods. Raising the coop off the ground by 12 inches or more prevents cold air from seeping directly through the floor from below. Straw bales stacked around the base of the coop create an insulating skirt against ground frost. Combined with the deep litter system operating inside, the floor insulation strategy works on multiple levels simultaneously. Now, here's something that changes how your entire coop performs, and it has nothing to do with materials or construction. It has to do with height. Specifically, where your chickens sleep. Warm air rises. Every chicken keeper knows this in theory, but very few design their coops to take full advantage of it. In a 6-foot-tall coop, the temperature difference between floor level and ceiling level can be 15 to 18 degrees Fahrenheit. That is enormous. A bird roosting 4 feet off the ground is not living in the same thermal environment as a bird sitting on the floor. They're in completely different temperature zones inside the same building. Chickens instinctively seek height when they sleep. This behavior is inherited from wild ancestors who roosted in trees to stay away from predators, but it also happens to serve them thermally. Studies confirm that birds roosting at 4 feet experience temperatures 10 to 15 degrees warmer than birds at floor level. The Amish design their roosting systems to maximize this natural advantage. The ideal roosting height ranges from 2 to 4 feet for standard breeds. Each bird needs about 8 to 10 inches of bar length to roost comfortably. Crowd them tighter than that, and they fight. Give them too much space, and they cannot huddle effectively to share body heat. For a flock of 10 birds, plan on 6 to 8 feet of total bar length arranged in a way that lets them press together without overcrowding. Bar material and shape affect how well chickens retain heat through the night. Rounded bars between 2 and 4 inches in diameter allow birds to wrap their feet around the roost completely, covering their toes with their belly feathers. This is not just comfort, it is a functional heat conservation mechanism. Chickens have a circulatory adaptation in their legs that reduces heat loss when they grip a perch correctly. When the bar is sized properly, their own body weight activates this system automatically. Multiple bars at different heights create thermal layering within the roosting area. Dominant birds claim the highest spots. Less dominant birds settle lower. A stepped arrangement, bars spaced about 12 inches apart vertically and 18 inches apart horizontally, lets every bird access a roosting height above the cold floor zone, regardless of their social rank. The difference between a well-designed roosting system and a poorly designed one shows up clearly in temperature measurements. A coop that registers 32 degrees at floor level on a cold winter night might show 50 degrees up at roosting height. That 18-degree difference is not trivial. It's the gap between productive, healthy birds and stressed, cold birds struggling to maintain basic body functions. But even the warmest, best insulated, perfectly designed coop will fail its birds if the air inside is not properly managed. This is the part that confuses most beginners. Ventilation in winter seems counterintuitive. Why would you let cold air into a space you are working so hard to keep warm? Here's why. A single chicken releases about 1/10 of a pound of moisture every day through breathing and droppings. In a flock of 10 birds, that adds up to 1 pound of moisture entering the coop air daily. Without adequate airflow, that moisture has nowhere to go. It builds up, condenses, and creates a cold, damp environment that is far more dangerous to chickens than cold, dry air. Damp cold is deadly. Dry cold is manageable. The Amish use a system called passive ventilation that moves air through the coop without creating drafts that blow directly on the birds. The principle is straightforward. High vents near the roof peak allow warm, moisture-laden air to escape naturally as it rises. Lower vents, positioned above roosting bar height but below the high vents, allow fresh air to enter. The air enters, warms slightly as it rises through the space, picks up moisture, and exits at the top. No fans, no mechanical systems, just physics doing the work. A reliable rule of thumb is 1 square foot of ventilation space for every 10 square feet of coop floor, but placement matters more than raw area. The vents need to be positioned so that incoming air. If fresh air is entering at bird level and blowing directly on roosting hens, you are creating a draft problem, not solving a ventilation problem. Those are very different situations with very different outcomes. Adjustable vent covers let farmers fine-tune airflow as conditions change.
The practical indicator of proper ventilation is the coop windows. If you see frost or heavy condensation forming on the glass, the moisture level inside is too high and ventilation needs to increase. If the air feels clean and dry inside, even on the coldest nights, the system is working. Here is a detail that surprises most people. Chickens generate about 2 BTUs of heat per pound of body weight per hour. A standard 5-pound laying hen produces enough heat in a full day to warm a gallon of water from freezing to room temperature. In a properly ventilated coop, that heat is captured and used effectively by the birds themselves, rather than being lost through moisture-laden air escaping poorly. Good ventilation actually makes the chicken's own body heat more useful, not less. Amish farmers use one beautifully simple observation to gauge air movement inside their coops: cobwebs. If the cobwebs in the coop are swaying gently, air movement is ideal. If they are still, ventilation needs to increase. If they are swinging widely, there is too much draft. It requires no instruments, no gauges, and no electricity, just attention to what is already in the room. Beyond what happens inside the coop, where the coop sits and how it faces has a major effect on how much heat it naturally accumulates and holds. This is about working with the land and the sun rather than fighting them. A south-facing coop captures dramatically more winter sunlight than one oriented in any other direction. During the shortest winter days, a properly oriented coop can gain an additional 6 hours of direct sunlight exposure compared to a north-facing structure. That translates to a 10 to 15 degree temperature increase inside, completely free, every single day the sun shines. Cold air pools in low-lying areas. Farmers call these frost pockets, and placing a coop in one is a mistake that costs birds and eggs all winter long. Raising the structure just 12 inches off the ground creates a measurable temperature difference at floor level, typically around 5 degrees. On a slight slope, cold air naturally drains away from the building the way water runs downhill. Some Amish farmers choose their coop sites specifically for this drainage behavior. Windbreaks matter more than most people realize. A well-placed row of mature evergreen trees can reduce the effective wind chill striking a coop by up to 75%. A single row of spruce trees 20 feet tall creates a sheltered zone extending up to 140 feet downwind. The Amish often plant these living barriers years before a new coop goes up, letting the trees mature before the building arrives. Planning ahead at that scale is not common in modern agriculture, but it produces results that cannot be replicated any other way. Window sizing on the south wall is a precise calculation. Too large and you lose more heat at night than you gain during the day. Too small and you miss available solar gain. The working ratio is roughly 1 square foot of south-facing glass for every 15 square feet of floor space. This allows meaningful solar heat gain during daylight while keeping nighttime heat loss within manageable limits. Snow can become an unexpected ally when it drifts against the lower walls of the coop. A 2-foot snowdrift pressing against an exterior wall provides insulation roughly equivalent to adding R10 to that surface. As long as the drifts do not block ventilation openings, they actively help keep the interior warmer. Nature is essentially insulating your structure for free whenever it snows heavily. Roof pitch is not just about aesthetics. A steeper pitch sheds snow faster, preventing dangerous weight accumulation, and creates more interior air volume above the roosting level. Each additional foot of airspace above the birds adds 2 to 3 degrees of thermal buffering. The air itself acts as insulation, smoothing out temperature fluctuations between the cold night and the warming morning. Building material choices also matter in ways that are not immediately obvious. Rough sawn lumber, the kind commonly used in traditional Amish construction, has a slightly irregular surface that creates microscopic air pockets throughout its thickness. It also tends to be cut to a full inch of thickness rather than the 3/4 inch standard of milled dimensional lumber. That additional 1/4 inch adds roughly 25% more natural insulation in the walls themselves before any additional insulating layer is added.
There is one more natural material that the Amish incorporate into their winter coop management that almost no one outside farming communities knows about. It looks ordinary. It feels soft and powdery between your fingers. But it does 3 separate jobs inside a winter coop, and it does all 3 simultaneously. Diatomaceous earth is made from the fossilized remains of microscopic aquatic organisms. Ground fine, it becomes a powder with remarkable properties. First, it absorbs moisture at a rate that seems almost impossible for its weight. A small handful can soak up a surprising volume of liquid, keeping the coop floor and nesting boxes dry even through the dampest stretches of winter weather. Dry conditions directly translate to warmer conditions for the birds. Second, diatomaceous earth creates a physically hostile environment for external parasites. Mites and lice, which become a serious problem in winter when chickens spend more time confined indoors, cannot survive in areas where the powder is present. The particles damage their outer coating through physical abrasion rather than chemical toxicity. No harsh compounds, no residue in eggs, no risk to the birds themselves. Just a natural mechanical barrier against pests that would otherwise compromise bird health and egg production through the cold months. Third, chickens actively use it. Given access to diatomaceous earth, hens will dust bathe in it voluntarily. In winter, when outdoor dust bathing in dry dirt is impossible, this indoor alternative keeps their feathers clean and properly conditioned. A hen with clean, well-maintained feathers retains body heat far more efficiently than a hen with matted or pest-damaged plumage. Amish farmers apply the powder with the same systematic thinking they bring to everything else. Rather than scattering it randomly, they focus on specific locations. Corners where morning condensation tends to accumulate, the area surrounding waterers where spills create persistent damp spots, the interior of nesting boxes where laying hens need dry, clean conditions to produce eggs consistently. Strategic application produces better results than general coverage. The timing of applications follows a regular schedule. Small amounts added every couple of weeks, rather than large amounts applied infrequently, maintain steady conditions throughout the winter. Children often take on this task as part of their daily farm responsibilities, learning by doing alongside adults who can correct their technique in real time. Now we come to the element that ties everything else together, the one factor that the Amish have identified as more impactful than any single technique or material: flock density. How many birds you keep in a given space. Each chicken generates roughly the same heat output as a 10-watt light bulb operating continuously. In a properly sized coop, that heat accumulates meaningfully. A flock of 40 birds in 160 square feet produces the thermal equivalent of 400 watts of continuous heating. That is real, significant warmth, generated entirely by the animals themselves, requiring no external energy input whatsoever. The tendency among new chicken keepers is to build larger than necessary, thinking more space means more comfort. This is a costly mistake in winter. A family that built a 300-square-foot coop for 20 birds discovered their chickens were shivering through cold nights, despite solid insulation and careful construction. Their neighbors kept 30 birds comfortable in half that space, simply because the body heat of the denser flock was sufficient to maintain livable temperatures. The insulation kept the heat in. The birds generated the heat. Both had to be present for the system to work. The practical guideline that Amish farmers have settled on through generations of observation is 4 square feet per bird for standard breeds. Smaller breeds can manage comfortably in 3 square feet each. Larger breeds may need 5. For every 100 square feet of interior coop space, plan on 20 to 25 birds. There is a lower limit to this as well. Cramming too many birds into too small a space creates stress, disease pressure, and social breakdown. Stressed chickens produce fewer eggs, they peck at each other, they compete aggressively for food, water, and nesting positions. The goal is density that generates warmth while still allowing every bird to move freely, access resources without fighting, reach a roosting position, and extend their wings without striking a neighbor. One Amish farmer documented something that illustrates this principle